This is Lab 1, Charge Tapes. In this lab, we will demonstrate the charged tapes exerting an electric force on each other and experiencing a gravitational force, and use this model to estimate the amount of charge on each tape necessary to float one tape above the other. This lab also explores polarization of charges, as well as how charges affect an object's behavior using Newton's second law and electric field and force. Some key concepts that will be necessary for understanding the physics behind this phenomenon is Coulomb's law, which states that electric force between two charged objects is directly proportional to the product of the quantity of the charge on the objects and inversely proportional to the square of the separation distance between the two objects. Similarly, the gravitational force is equal to the mass of the tape times the acceleration due to gravity in the negative y-hat direction. To find the charge on one tape, we will use Newton's second law. On the floating tape, there's no external force as the tape is not moving. Therefore, the magnitude of the electric force by the bottom tape equals the gravitational force of the upper tape. We also know that like charges repel and opposite charges attract. So the procedure for making the U-tapes includes taking a 0.2 meter strip of tape and placing it on a smooth surface, and taking another strip of tape with a handle at the end and laying it on the base tape, and quickly stripping out the upper tape and carefully putting it aside. And we repeat these steps to create another U-tape. To quantify the charge, there's three methods that we can use. We can place the two U-tapes near each other, hold our hand near one of the U-tapes, or rub a pen on our hair to give it a positive charge, and then place the U-tapes near the charged object to quantify the charge. In all cases, we assume that the charges are evenly dispersed on both pieces of the tape and have an equal magnitude of charge. Our results show that the U-tapes repel each other, suggesting they have similar charges. The U-tapes are attracted to the positive pen, suggesting that they have a negative charge. The floating tape, the procedure includes suspending one of the U-tapes from an object such as a desk, and then holding a second U-tape above the first one until it begins to float, and then recording the distance between the two U-tapes until the top floats. We assume in this case that the tapes are modeled as point charges to use the gravitational and electric force equations we'll see later on. Here we have the measurements that we will need to do our calculations. We have the distance between the two tapes, which is 0.0198 meters, the length of the tape, which is 0.2 meters, the tape width, which is 0.0232 meters, and the surface area of the tape, which is the length of the tape times the width of the tape, which is 0.2 times 0.0232, which is 0.00464 meters squared. Here we have the calculations for the problem. As mentioned above, we use Newton's second law to find the magnitude of the electric force, which is equal to the magnitude of the gravitational force, which is negative 1.96 times 10 to the third newtons in the y-hat direction. Rearranging Coulomb's law and solving for charge gives us Q equals 9.24 times 10 to the negative 9 Coulomb. To find the fraction of the electrons that give away atoms, we first need to find the deficit electrons, which is equal to the charge that we found before divided by the charge of an electron. To find the number of atoms on the tape, we take the surface area of the tape and divide it by the area of one atom, approximately 1 times 10 to the negative 20 meters squared. Using this, we can set up a ratio between the deficient electrons and atoms to get 1.224 times 10 to the negative 7 atoms per electron. We can also model this phenomenon using glow script. First, we have our contents listed out over here. Then we represent Newton's second law by calculating the gravitational force and setting it equal to the electric force. Then we use the same method of rearranging Coulomb's law to find the charge, and we finally plot this on our glow script viewer. The blue charge represents the floating tape, and we can see the green charge represents a charge by the lower tape, and the blue arrow represents the gravitational force, which are equal in magnitude and opposite in direction. The calculated charge equals the handwritten calculations, which is 9.2 times 10 to the negative 9 Coulomb. Some assumptions we have to make in this model includes ignoring air resistance on a moving object, treating the long tape as a point charge with a charge concentrated at the center, and assuming each U-tape had the same amount of charge evenly distributed along the length of the tape. Now, what would happen if the charge on the proton electron were flipped? The tapes would still have like charges, but would repel the positively charged pen. The polarization would also be in the opposite direction. Why is it important to handle the charge tape as little as possible? The charge tapes have an electron deficit. When coming in contact with hands, electrons could transfer to the object, changing the object to a positive charge. This decreases the magnitude of the charge on the tapes, and since the magnitude of the charge is directly proportional to the distance, it would take a smaller distance for the upper tape to float above the lower tape.